And I don't know if that means yes or no.
Dropping classes
Oh,
every
yeah.
2 seconds.
Oh, okay. Well, we'll see how it shakes out. Okay, so we're gonna write some proofs today. Before we do that, I do have assignment 1 ready, and I'm gonna hand it out at the end of class. So don't leave without making sure I hand this out to you. It's also posted to Canvas already. One of the things we're all doing this week is making sure that we read through that academic integrity standards, and then go to Canvas and click on the contract to sign. There'll be a button that says, take the quiz or whatever. It's just a survey. And if your name is one of the names in the right column, you should do that. I think it doesn't take very long to do. It takes like 2 clicks, okay? Okay. Are there questions from last time? Okay. All right. This is going to be pretty fun. So we're going to write proofs. And there's sort of 3 basic techniques that we have. And a proof is just an argument. You're just writing a convincing argument so that the reader will be convinced of the truth of whatever you're proclaiming. So the basic kind of statement that we prove is an A implies B statement, or if A, then B. So some examples of these types of propositions would be if n is even, then n squared is even. Or if n squared is even, then n is even. And we should note that these are different. So the order of the implication matters. And the square root of p is an irrational number for every prime number p. That doesn't look like it's in the if-then form, but we could put it in that form by saying if p is prime, then the square root of p is irrational. So these all happen to be true, and we're going to prove them all, or at least we'll prove the first 2, and in the third one we're going to prove that for the prime number 2. In order for something to be true, it has to always be true. Like, if I want to show that if n is even, then n squared is even, it's not enough to just show that when I square a bunch of different even numbers, I get an even number. Like 2 squared and 4 squared and 6 squared and 8 squared. I could check a million evens and show that their squares are even, but that doesn't prove it because there are infinitely many. I cannot possibly check them all. So I'm just going to emphasize this right here. An example is not a proof. Finding an instance where something is true does not mean that it's true all the time. An example can be a great way to start out. Like if I'm trying to prove something and I'm just trying to wrap my mind around the statement that I'm working with, I might start with some examples just for myself to kind of see what's going on. And that might help get me started on how to approach writing this proof. So just some general guidelines around writing. There's a longer list of some guidelines at the end of this section. But you always need to give supporting statements, supporting evidence for the statements that you make. We should check spelling and grammar. We should be writing complete sentences. And yeah, we're gonna include symbols. Like I'm not gonna write implies that when I can just use this little arrow. Like that's often we use mathematical symbols to kind of cut down on how many words that we have to include. But they're still sentences that make sense. I always tell people this, and I don't know if people ever do this because I don't really because I often still get assignments where things like sentences just don't make sense syntactically. Like that's not a sentence, But read it out loud, actually out loud. And what I tell people is if you're writing an argument, right, and you go and you're looking through your work, if you read it out loud and you find that you are inserting words to make it an actual sentence that seems to have flow, maybe that word should be included in the writing itself.
Also, if you're verbally having an argument and you're just spewing gibberish, that sort of weakens your position a little.
Probably, yeah. I would agree with that. I always include as many clarifying steps as possible. Like, I err on the side of including more detail than less. Because you want to, when you're writing something, and I would say this is good advice for writing in any class, don't make the reader do all the work, right? You want to make the reader do as little work as possible, and you're just sort of guiding them through, right? Walking them through your argument. So I err on the side of including more details than less. And, and then there's like formatting things. If I have a long string of equations, I'm not going to do it in a paragraph. I'll probably like display it nicely centered or something, just to make it, easier on the eyes. But we're going to look through some different types of proofs to write. These are different approaches. Depending on what you're trying to prove, one statement might be easier, one approach might be easier than the other. So the first is a direct proof. And then these other two, these are both two types of indirect proof. In a direct proof, when we're considering proving the statement A implies B, or if A, then B, then in a direct proof, you just assume A is true. So you get that for free. And then you show that B has to be true. Sometimes going a direct route is hard, and it might be easier to take one of these other approaches. The contrapositive, we went over what the contrapositive is. Like, so if A implies B is if that's a proposition, then it's contrapositive. Is not B implies not A. So sometimes that's easier to prove. And so basically the right method is whichever one kind of gets the job done for you. And then proof by contradiction is it's probably one of my favorites to do when it will work. With the proof by contradiction, you just suppose that what you're trying to prove isn't true. Suppose this is not the case. And if from that you can contradict something that we know is true, like, well, if this weren't the case, then 3 would be an even number or something, and obviously 3 is not even, something like that. And then that makes us go back and say, well, our assumption in the beginning must have been false. So we're gonna see each of these at work today. We're gonna start off by proving that if n is even, then n squared is even. A lot of the time, not always, but a lot of the time I will say what approach to take, like prove directly or prove by contrapositive. And usually when I say that, it's because this is the way that's most likely to work, or will take the least amount of work for you to do. So there's a lot of like even odd proofs. We're going to kind of start off just by working with numbers and the integers as our basis for learning how to write proofs, because it's a familiar setting for us. So one thing, you'll get this for free, right, in all settings. An even number, an even integer, is one that can be written as 2 times n, where n is any integer. Right, any even integer, that's what makes it even. It has a factor of 2. You can pull out a factor of 2, basically is what this says. An odd integer, and I'll be a little bit less wordy, is something, so every integer is either even or it's odd, right? Even, and they alternate. So you take an even number and you add 1. Any odd number can be written in that form, where n, again, is some integer. When we're talking about integers, we often use n's and m's and k's and j's. You can use whatever you want. There's just certain conventions that I tend to adhere to. So in this example, we're gonna prove that if n is even, then n squared is even. So let's begin. We're going to do this directly, so we're going to suppose n is even. That's the only thing we're supposing here. So where does that get us? What can we do with that?
We have a good starting foundation. The foundation is strong.
Yes, the foundation is strong. Suppose n is even. What is an even integer?
Anything that is factor of 2.
Right, has a factor of 2 or can be written as 2 times some other integer.
Yes.
So we could say then n equals, now I can't use n again because n is my any old integer here, even integer. So I'm going to say it's 2k. For some integer k. The only thing I'm assuming about k here is that it's an integer. So that's what we know about n. What is it that we're trying to get to?
We're trying to get that every n squared is even.
Right, that it's even if n is even, right? So we're trying to get to a statement about n squared. So here we have this equation with n. So let's do this. Let's observe. If n is equal to 2k, I have this equation here. If I square both sides, then n squared is 2k squared. What's 2k squared?
4k.
Squared. Yeah, 4k squared, yep. So n squared is 4k squared. Now, I'm going to do something that's going to seem odd right now, no pun intended, but I'm going to just really drive this point home for the reader. And I'm going to say that means that n squared is 2 times 2k squared. The reason I wanted to pull out that factor of 2 is because we know, the thing we know for free is like, if something's even, then you can write it as 2 times some integer. And actually, that goes both ways. If something is 2 times some integer, then it's even also. Like, those are equivalent statements. So the only thing I'm left to do here is just to point out that, you know, k was an integer, so 2k squared is an integer. And so n squared, which is equal to 2 times 2k squared, is even. As desired. That's what we wanted to show. Huzzah.
Much fanfare.
Yes. Questions so far? Anybody not convinced? Or is there a question on a particular step we took that seems like we left out a detail or... So notice, you know, I'm using words. I'm constructing an argument. I'm not using too many words. Like, it was, you know, totally okay to just have this section on the bottom or in the middle here where I've displayed these equations, each of which, you know, implies the next one down. I don't have to keep writing, like, all of those in English. But then I include a nice concluding statement. You want to let the reader know when you're done. Like, you know, you want to declare victory at the end, you know, so that it kind of make your point. Want to do another one?
Yeah.
Yeah, okay. So we're going to show that if n squared is even, then n is even. So what we're doing is we're taking the last one and we're just reversing the implication. As it turns out, that's not always true, right? If A, then B like if A implies B is true, it's not always the case that B implies A is true. But if when you just reverse the implication, we call that the converse of the statement. A lot of the times you can't reverse the implication. Like it's not always true. Like all chickens are birds, but not all birds are chickens type of thing. In this case, when we reverse the implication, it is true, and we're going to use the contrapositive to help us with this. If I'm going to prove something by contrapositive, the first thing I'm going to do is actually write down what the contrapositive statement is. And I'm also going to let the reader know that that's my approach. So I'm just going to say, we will prove the contrapositive. And then I'm going to write it down. So, okay. What should be the contrapositive of if n squared is even, then n is even? That's the converse.
If not even, n squared is not even.
Yeah. Yeah. So n squared is even, n is even, right? Those. So here's our A implies B, right? So then not B is, say that again?
Not B is if n squared is not even, or if n is not even.
If n is not even, yeah. So what if an integer is not even, then we know it's odd. That only works for whether or not it's a multiple of 2, so like it doesn't work for multiples of 3, but we know for sure if n is not even, then n must be odd. So if n is odd, then what?
Then n squared is odd.
Yeah. And we're going to prove by contrapositive because it's really the way where it's possible. Like if I start off assuming that n squared is even, then to get to a statement about n, I'd have to take a square root. And then you end up with this expression that has the square root of 2, which isn't even an integer. Okay, like, so that becomes really cumbersome to work with. But if I start out making an assumption about n and then moving to n squared is a lot easier. So let's suppose n is odd. What does that get us?
N squared is not?
Well, that's where we hope it gets us.
Yeah.
That's what we're going to prove.
Should be.
But what do we know? I mean, that's the goal. If we're going to write a proof, we need to do more than just say this is true.
Is equal to n
2k plus 1.
Yeah, 2k plus. It's got to be one more than an even. So n is equal to 2k plus 1 for some integer k. And it's really important that I state for some integer k. Like, that needs to be in there. Because I could write 3 as 2k plus 1 as long as k is, what, a half or 3 halves, right? So, or sorry, 3. I could write 2 as 2k plus 1 if k is a half, right? But then k is not an integer. So, like, this part is actually important to include. What do we do now? What's our goal? Like, what's our end goal here?
To n squared.
Yeah. We want to get to a statement about n squared. So what do we do?
square both sides again?
Yeah, so let's observe. That implies that n squared is equal to 2k plus 1 squared. How do I square 2k plus 1? Need just a little algebra here.
4k plus 2.
Not quite. Let's see. 2k plus 1 squared means...
We do 2k plus 1 times 2k plus 1.
Right.
Oh, yes.
We got to FOIL that out. So you might recall You might just like the acronym FOIL, or you might recall I'm a big fan of the table approach here. So 2k times 2k,
4K.
4k squared. K times k. And then 2k times 1 is 2k. 2k times 1 is 2k. 1 times 1 is 1. We have our like terms right here. So this is 4k squared plus 4k plus 1. What is it that we want to show about n squared?
Say that again.
Yeah, right. We want to show that it's odd, right? That our hope is to conclude that this is odd. So I'm actually pretty psyched to see that on the end.
Yeah, because the amount of like the other times it's gonna be.
Yeah. So okay. What makes something odd?
It's one more than even.
One more than an even. So one more than 2 times an integer. So from this part, like a lot of sometimes what we do is just try to like almost unsimplify something in a creative way. It's not about having the simplest expression. It's about having an expression that makes the point I want to make. If I'm trying to conclude that this is odd, what I want to do is show that it's 2 times an integer plus 1. So from these first two terms, I'm going to factor out a 2. What goes inside these parentheses? 2k squared plus 2k. Now, we're just about there. It's not enough to say it's 2 times something plus 1 to be odd. It has to be 2 times some integer to be odd. So the last thing we want to do is just say, well, we know that k is an integer, so that means 2k squared plus 2k is an integer. Like if you take an integer and you multiply it by 2, it's an integer, right? You're not going to create a fraction by doubling an integer. If you square an integer, it's going to be an integer. If you add 2 integers, it's going to be an integer. It's not going to give you fractions when you add 2 integers. So we just want to kind of include that statement. And so that means that n squared, which is 2 times this integer, plus 1, is odd, as desired. Now we're just about done. I mean, we've reached a conclusion here. But we proved this by contrapositive. So what was the original statement we wanted to prove?
N squared is even.
Other way around.
If n squared is even, n is even.
Then n is even, yeah. So I'm just going to point that out, right? So by contrapositive, if n squared is even, then n is even.
How do we know for sure that the contrapositive is true? Is it just something that's generally true? Or?
Oh, well, we proved it last class. We made a truth table for P implies Q and then compared it to not Q implies not P. So they're logically equivalent. Yep. Other questions? Okay. All right, this next one is one of my favorites. Are you ready for it? It's going to take a while. So, when you prove something by contradiction, you start out by supposing that what you want to show isn't true. Then you hope, as a result, like that if this is the case, then the world would come crashing down around us as we sit here. And since that's not happening, must be we were wrong to assume that this isn't true. That's sort of the basic idea. What's tricky about proof by contradiction is we don't know exactly what the contradiction is that we're going to reach. So we kind of have to be a little vigilant about, paying attention to what we're doing. There's not like a clear roadmap. We just know if we're going to prove something by contradiction, there'd be some contradiction that we reach at some point. So we're going to show that the square root of 2 is irrational. And to get us ready for that, let's talk about a rational number. Does anybody know what a rational number is?
It's like all real numbers, right? And,
It is
if
not.
Any real number that isn't, like, doesn't go on forever.
Sorta. Not entirely. It's because like 1/3 is rational, but its decimal expansion goes on forever. So the root word of rational is ratio. And so it's one that can be written as a ratio of 2 integers. So like fractions. And I'm going to go further than that. If I have a number that's rational, like let's say I throw out the number like 2/4, you would say, why do you call it 2/4 when we could call it
1/2.
1/2? So not only is a rational number one that can be written as a ratio of integers, but it can be written as a ratio of integers in lowest terms. So like it could be written as a reduced fraction. An irrational number is just one that cannot be written as a ratio of integers. Okay, so now I think we have the foundation to go on here. We're going to prove by contradiction that the square root of 2 is irrational. So if I'm proving by contradiction, I'm just going to start out with, suppose it's rational, right? Like suppose this statement is not true. That means that square root of 2 would be irrational. So suppose for contradiction, that the square root of 2 is rational. And I'm letting the reader know, like I'm going by, this is what I'm going for. I'm going to reach a contradiction. I'm letting the reader know that right up front. What does it mean to be rational?
That can be written in two rational number or two integers over another.
Mm-hmm. Yeah, so as a ratio of integers. And I'm going to kind of add that stipulation that it can be written as a reduced fraction, right? So then let's see. We can write it as a reduced fraction. And what it means to be written as a reduced fraction is that the square root of 2 is some fraction a over b. If this fraction a over b is reduced, what makes a fraction reduced?
Moving it from a larger state to a smaller state.
Okay, yep, it's because by like canceling out common factors and stuff. Yeah, so what makes it really reduced is that there are no common factors left, right? Like you put it in the smallest state possible.
What makes it reduced is that it can't be reduced any further.
That it can't be reduced any further, and that what's true about A and B, when you compare them, is that they have no common factors. So that's part of our assumption. A and B don't have any common factors. Okay, now let's do some stuff.
I thought you were going to write, now let's do something.
Well, we could. That would be acceptable. So,
Informal proof.
yeah. So we have this equation, square root of 2 equals A over B. I'd want to work with integers and not radicals, so I'm going to square both sides. How do you square a fraction?
Square the entire thing.
Yeah, square the top, square the bottom. So on the left side, we just get 2, because that undoes the radical. So we have A squared over B squared. Now, I want to work with integers, not fractions. What can I do? Multiply, well, not by the reciprocal, but by the denominator, right? Let's just clear denominators. So we have 2b squared equals a squared. Now we're going to rely on a result that we just proved. A squared is 2 times b squared. What kind of number is a squared, if it can be written as 2 times b squared? What?
Even?
Even, yeah. So, because since it's 2 times some integer, we know a squared is even. And if a squared is even, what does that mean about a?
A also has to be
Yeah, we just proved that. If a is even, how can we write it? What does an even number look like?
2 times the number.
2 times some integer? Yeah. So, let's see. Then a is even. So we can write a equals 2k for some integer k. Great. You'll notice you might be running out of room a little bit, but
saw the other page.
I saw that coming, so we have plenty of space. So I'm going to put a little star next to this equation here, the 2b squared equals a squared. So if a is equal to 2k for some integer k, what I'm going to do next is substitute a equals 2k into that equation. So 2b squared equals 2k squared. You might feel an urge to do something right now. You're looking at this equation, you're thinking, what do I want to do? Yeah, we don't really, it's not a binomial, so we probably don't need to FOIL, but just like multiply that side. 2k squared is what? 4k squared.
Why does it hold on to its squared?
What's that?
Why does it hold on to the square?
Well, it's the k is squared, so 2k
Oh, that's right.
squared. I'm just going to finish writing it out, but yeah, 2k times 2k. So we have 2 times 2 times k, and that's 4k squared. Now what? What's that?
They're both squared.
Yeah, that's okay. They are both squared.
Divide by 0.
I'm not going to divide by 0. We don't do that.
Divide by 2.
Divide by 2. Yeah, let's reduce this. So if we divide out by 2, what's our result?
B squared equals 2k squared.
Mm-hmm. Okay. Spend a minute or two looking at this equation and think about what has to be true about b squared.
B squared
Has to be
has to be
even.
even.
Yeah. Yeah, because it's got a factor of 2. So this means that b squared is even. What does that mean?
So it can be represented in the same way that the other one was?
Well, b squared is even, right? Right, 2 times something.
But if they're both even, then you should be able to have a common denominator of at least 2.
If both of what is even?
If
If
both.
A squared and B squared are even,
Yeah.
they'll have a common factor of 2.
But, well, our fraction doesn't have a squared and b squared. It has a and b.
That means they're both even.
Okay, so I guess what I'm getting at is we just said that b squared is even. So what do we need to write next?
2k squared is even.
Well, we know that, true, yep.
We can substitute out b for 2x.
B squared is equal to 2k squared is even.
Yeah, b squared is even.
It can be written as 2b or 2k, 2 times k,
What can be?
b squared.
Well, it's 2k squared. There's a conclusion we can make just by knowing that b squared is even. Forget everything else that we've done in this proof.
Means a squared is even? Or b is even. B is even.
Thank you. b is even. We needed to write that detail. That's important. And yeah, we could say b is equal to 2 times j or something if we want, but we don't need to anymore. We don't actually have to go further. We don't have to go that far as writing b. We know that b is even. What did we show earlier?
A is even.
That a is even. So what do we know about a and b?
They have a common denominator.
They have a common factor, yeah, or common divisor. So now we have established that a and b are both even, which means they have a common factor of what?
2.
Yeah. So what? They have a common factor. Great. How does that help us?
If they have a common factor of 2, then they can pretty much constantly be reduced to the lowest possible form, right?
Just cancel out the 2? Yeah. Yeah, so we're looking for the contradiction, right? We said we're going to prove this by contradiction. So far we've just made conclusions, right? What have we contradicted?
That they can have no common factors.
Yeah. Yeah.
Square root of 2 is the lowest term.
Right, like that fraction could not have been written as a reduced fraction because we assumed that they could be written as a reduced fraction, and once we make that assumption, a few steps is all it takes to show that, as it turns out, they must share a common factor of 2. Now, somebody might say, well, just cancel out that common factor. Then it's reduced. And you can't. Like, let's say, okay, we'll cancel out the common factor of 2, so then we have a new fraction, a1 over b1 or something. You just do this again. You could show that there will always be a common factor of 2. In Latin, the proof by contradiction is something like reducto ad absurdum or something. Like you just keep going. Like it's like an infinite.
Harry Potter language.
Yeah, kind of. Yeah. So let's see. We need a conclusion. So that's okay. So this means that the square root of 2 cannot be written as a reduced fraction. And it follows that the square root of 2 is irrational. There's a story that gets told that is almost surely apocryphal. So, it's probably not true, but I'm going to tell it anyway. The story goes that the first guy who proved that the square root of 2 is irrational, back in ancient Greece, like the time of the Pythagoreans, the math community was more like a cult and a mob. Like, they were serious and violent, I think. They didn't believe also that irrational numbers existed. They thought every number was rational. Maybe we haven't found the fraction for it yet, right? But they thought that irrational numbers didn't exist. So the story goes that the first guy who proved that the square root of 2 is irrational, they took him out into the Mediterranean and dumped him overboard. But the truth got out anyway. So it has a happy ending.
They love their numbers.
Yeah,
They do.
At what point would that fulfill? I don't know.
What's so funny is the golden ratio is an irrational number. Is not actually rational.
The cost for success.
Do you guys want to do another contradiction proof? They're pretty fun. What?
It looks like we have to.
Yeah. Well, yeah, but if you want to, then it feels more fun, right? Okay. So we're going to show that there are infinitely many prime numbers. There are, in fact, infinitely many primes. There's no set pattern to them also. The prime numbers are how the primes are distributed through the integers is an area of active mathematical research. It's actually super exciting and a lot is not known about them. But we do know that there are infinitely many.
What's the highest one?
What's that?
What's the highest one?
There is no highest one.
Well, there's got to be a highest one found so far.
Oh, sure, yeah. It's in the hundreds of digits, I think. Yeah. And now when they find a new highest prime number, it's always found by computers.
Bust out the champagne.
Yeah.
My favorite prime number is 1, 13 zeros, 666, 13 zeros, and then 1 again.
That's a really unlucky number.
That is a fun
One,
number.
hold on. I'm going to write it down. 1,
13 zeros.
six, six, six.
Yep. And then 13 zeros. And then 1 again.
Okay.
That's a prime number.
Okay, I'm going to remember that.
This is in my notes.
Okay, so we're going to prove this by contradiction. If we're going to prove this by contradiction, what is our opening statement?
There is a finite amount of prime numbers.
Yeah, let's suppose there are finitely many prime numbers.
Is that a word, finitely?
Yep.
I like that word.
Okay. You could say a finite number of, if you want. So if there are finitely many primes, then you can put them in a list, right? A finite list that will end. So we're going to do that. Are you ready for this?
I like how the paper for this one is shorter than the paper for the other one.
Yeah, this one doesn't take as long. Then we're going to list them. I guess I could say we can list them would be a better way to write this, but we're going to. I'm going to start P1, P2, P3, all the way up to Pn. So there are n primes. So this proof by contradiction is going to be a little bit more constructive in that we're going to make up a new number from the ones we have here and show it's the existence of that number, which must exist, will imply that there must be some prime that we missed on our list. And if our assumption is that we could put them all on a list and then we conclude, oh, we must have missed one, then that is enough. That's a contradiction, because even if I just add that one to the list, we'd be able to make another new one and conclude that we missed one again. And that could just continue, ad infinitum.
Is that what the computers are doing when they're searching for new ones?
You know what? I think usually when they search for a prime, they'll stick. There are certain types of primes, and one is called a Mersenne prime. And a Mersenne prime, I think, is 2 to the n, and then -1 or something, like, is of that form. Not that every number of that form is prime, but primes that can be written in that form are called Mersenne primes. And I might be slightly off on what the form is, but it's something like that. So there are different searching algorithms, and then they just I don't know exactly what I don't know the efficient algorithm might be to determine if a number is prime, but I know there probably isn't a super efficient algorithm, because the fact that primes are really, really hard is what makes our encryption, algorithms work.
So they don't just have a computer counting up, and every time it gets to a number, it divides by 2.
I don't think so. I think they stick to different types of primes, and yeah. All right, so here's our finite list of primes. Let's consider this new number. I'm going to call it capital N. And this number, capital N, is going to be obtained by multiplying all the primes in our list and then plus 1. Okay, let's say I take this number, big N, that we just made. If I tried to divide it by P1, what would the remainder be?
P.
No. No, well, so N is this multiple of P1 and then plus 1 left over. So if I were to divide N by P1,
There would be the rest of the.
I get a remainder of 1. Yeah, because it's 1 more than a multiple of P1, right? That's kind of what a remainder is. If I were to divide it by P2, what would my remainder be? And P3? All of them. It doesn't matter which one of these primes I try to divide it by. It will leave a remainder of 1. So let's sort of get that out in words. So for each prime in our list, I'll call it P sub I. We will get a remainder of 1 when we divide N by P sub I. So this means that N is not divisible by any of the primes on our list, because each time I'll get a remainder of 1. That forces us to conclude 2 things, or it forces us to conclude one of 2 things. One of the following has to be true. Either big N itself is prime, because it's not divisible by any of our primes, or it has a prime divisor that's not on our list.
And because N is not on the list,
Yeah. Like, either N is a prime that's not on our original list, or if it's not prime, it has a prime divisor that was not on our list to begin with. either way, our list of primes is incomplete. And this contradicts our assumption that we could list all of the primes. So what do we conclude?
That there are infinite primes.
Infinitely many primes. How's that? Okay.
That hurts.
Well, then I've done my job. The last thing I want to talk about today when we're writing proofs is the if and only if. We've all the proofs we've written have been if then, right? If A, then B. If you're writing an if and only if, and an if and only if we can denote with the double arrow there, that each implies the other, you have to write two proofs. An if and only if is equivalent to both of these, that an if then being true as well as its converse. So if you're going to prove an if and only if, you really have to do two proofs. Here's part one, A implies B, then turn it around, B implies A. If you've done both of those, then you've written an if and only if. So, for example, we proved a couple things. We proved that if n is even, then n squared is even, and then the very next thing we did was if n squared is even, then n is even. We proved both directions of that implication, and so if we combine what we did in examples 1.8 and 1.9, what we have proved is that an integer n is even if and only if n squared is even. I can't stress enough, and in fact I'm actually just going to write out these words. If I need to prove an if and only if, if I need to prove an if and only if proof, then I need to write two proofs. One for each direction. Not all the time, but sometimes, once you've got one direction down, you could sort of use that and those same ideas to help you go in the other direction. You just have to make sure, like when we did the n is even, then n squared is even, and then went the other way, we took a similar approach each way. But when we proved the other direction this time, we were like, oh man, it's hard to prove the other direction directly, so I'll take the contrapositive. Like, you just have to be careful, treat each one like it's a brand new proof. And So I'll stop talking right now. But every time I give an if and only if, like, I get some in, probably like maybe almost half the class will like prove it in where, turn something in where they've only got half of it done. Because it's easy to think you're done when you've reached a conclusion, right? You proved one direction, so then you probably worked really hard at it, so it feels like we're done. But if it's an if and only if, like, just be really careful. Make a note to yourself. Are there questions? Okay.
Can we prove by contrapositive that the Earth is flat?
No.
Okay.
You can't prove something that is not actually true.
Okay.
Whew. That's a load off my mind. Okay.
That's why the flat earth theory